下面开始我们第二个主旨报告来自小米的丹尼尔教授。首先我先简单介绍一下丹尼尔的个人情况。丹尼尔 Pro 是著名的开源语音识别工具标 Kaldi 的主要开发者和维护者。他在2003年在英国剑桥大学取得博士学位。之后在2003年到08年在 IBM 华盛顿研究中心从事研究。2008到2012在微软研究中心从事语音识别工作。2012到2019在约翰霍普金斯大学语言和语音处理中心任研究科学家和研究教授。2019年起担任小米公司首席语音科学家。目前从事下一代工作的研究，下一代 Kaldi 工作的研究。那么 Kaldi 呢，在工业界和学术界被广泛使用。刚才崔总也提到了相关的一些背景。那么 Kaldi 工作的引用量高达6000多次。那么Danny Povey 本人的论文引用量已经接近了36000次。下面我们有請Daniel 来进行他的报告。Hi, Prof. Daniel. Maybe you can start the
Sure.
presentation.
Cool. Let me just share the screen. So cool. You guys can see my screen, right?
Yes.
Is this question?
Yeah. Just made a message.
Okay. Cool. So my talk is just a summary of this last year's progress, what we've been doing in our team. So we have, I'm afraid I don't have a list of members, but we have like me plus 7 other people here. If we include my assistant, I think me plus 6 devs. I may have the number wrong, but it's about that. Here's the overall summary. So we switched focus from CTC plus attention decoding to transducer decoders like RNNT. The reason for this is that we're focused on practical inference. Like we want it to be productizable, and attention decoding is very hard to do with high parallelization because the decoding algorithm is kind of complicated. So if you want to have a server that is serving like 100 threads, that's really hard to do considering GPU memory. So we're focusing on RNNT, which has similar word error rate, but is a bit more practical. We have a lot of incremental improvements to word error rate and to training speed. And we also created a deployment framework, like an inference framework that we call Sherpa, that supports decoding multiple streams in parallel on CPU or GPU. So it's mostly geared towards server-based products, but it also should support some embedded scenarios. So our general goal is just to be the best possible ASR suitable for making products out of. And what we're mostly currently working on is we keep trying to improve our deployment framework, Sherpa. Our big challenge right now is we have to get contextualized ASR thoroughly working, because these end-to-end models, and particularly RNNT, they work great on matched data, like if you train on LibreSpeech and test on LibreSpeech, but they don't always work so well if there's a mismatch, meaning the combination with language models is a challenge, and we're working on that. And there's been a lot of recent papers on that. There was a paper recently from Tsinghua and some company, Meituan or something, and we're implementing things like that. Plus, we're just generally improving our models. We have various, like, I'll describe various papers and things like that, modeling improvements. But our overall goal is ASR that's good for product. We already have really good word error rates. I'll share some of them later. And our training is very fast. I think that's one of the best advantages of our setup over other people's setups, that partly because we don't have tons of GPUs. We're very cost conscious, and we're focused on getting the best word error rate with a minimal number of training epochs and a minimal number of GPUs. So you won't see us publishing with with 500 epochs like some other people do. We're mostly training for 30 epochs, and we have like as good word error rates. So in the rest of this talk, I'm first going to summarize the current status of our system, what techniques we're using, and so on. And then I'll go through briefly some of our current kind of papers, some of our technical improvements that we've done recently. And then I'll try to give you a quick overview of our inference framework called Sherpa. Okay. So now we have two slightly different versions of our system, depending if the scenario is like batch decoding or online real-time decoding. So for batch mode, our encoder is just a conformer. Our older recipes before like today, we're using a modified conformer with a few changes. We have something we're introducing this weekend, basically called a zip former, which is a highly modified conformer with a unit-like structure. I'll describe it a little bit later. And actually, we have something coming up that's even better than that. So that's the encoder. The decoder is a transducer, as in RNNT, but it's not actually recurrent. It's not an RNN. We use the so-called stateless RNNT, where the decoder sees only a limited number of symbols of history. Now, normally when people think about RNNT, we think about the decoder as encoding this long language model history. It seems that that's not what really happens. It seems like if you truncate the history to just a couple of tokens, it really makes very little difference to the outcome. It seems like what the system might be doing is trying to do the language modeling inside the encoder. Strange. Okay. So our normal decoding mode is without language model because we don't get huge improvements from language model. But we do also sometimes decode with language models, and our tools definitely support it. That we can decode with finite state automata or FSTs, and decode with neural language models too. And that's important for real applications. Okay, so our streaming version of our system, one of them is a streaming conformer with a blockwise attention mask and also a causal convolution, kind of like what WeNet does. Another version is an M former. I think this came from Facebook or one of those big companies. It's a kind of conformer with a method of summarizing the history of the attention. The word error rate is a little bit worse than conformer, and it's slower to train, but it uses less memory in inference time. The third one is LSTM. LSTM's advantage is it uses very little memory in inference. So if you want to decode with 200 streams on one GPU, you could in principle do that. But it generalizes much worse if the amount of training data is small. However, I'll show you results later that if you train on 10,000 hours of data, the degradation in word error rate is not too bad. Here's some results from the things that I just mentioned. So the top one is the batch mode, right? Non-streaming. So these are all trained on LibreSpeech, but if it says plus GigaSpeech, it's trained on GigaSpeech too. So the top is a standard conformer, 2.57 on test clean. Then with GigaSpeech, it's 2.0. And if we add LM language model rescoring with a neural net LM, it's 1.8. I think we more recently have a better system than that with zip former. But so our streaming version, the WeNet style chunked attention, we get 3.4. So you can see that there is a substantial degradation from streaming mode, from 2.6 to 3.4. If we add GigaSpeech, it's 2.81. convenformer is a little bit worse than conformer, but it has the advantage that you could run more decoding streams. Then LSTM is, you see, it's even worse. It's conformer is 3.4 on just Libri, and then it's 3.65 with LSTM. And on GigaSpeech, oh, now I'm seeing that on GigaSpeech is actually about the same as LSTM. It's even a little bit better. It's 2.8, sorry, the same as conformer, 2.81 versus 2.73, although it's a bit worse on test others. So the point is, if you have really tons and tons of data, LSTM is not that bad for streaming mode. It's not as good as, you know, batch mode conformer, but it's not terrible. And then plus LM rescoring, we get down to 2.2. I mean, a user probably wouldn't notice these differences in word error rates, you know, 2.2 versus 2.0. So it's not really that terrible. Okay, so about decoding with language models. We don't always decode with a language model because we get very good word error rates without that. And the RNNT seems to mostly like learn the language model of, sorry, the encoder, the conformer encoder seems to learn the language model of the training data. But we still get some improvements from the language model. I'll show you the numbers here. So let's see, the top side is LSTM acoustic model. The lambda 1 and lambda 2 are the scales on the language model, and then the internal language model. So with RNNT, because the model learns the language model, you have to subtract an estimate of what the model learned. So the bolded number there is 2.28. That's where we use a bigram estimate of what the a bigram estimate of the internal language model, and you subtract that. So you know that's pretty good. Where the language model is definitely helping, and we can get down to 1.82 if we train on GigaSpeech also. So again, it's not bad. So in the near future, we want to focus a little bit on using language models where there's a big mismatch between training and testing, because this is always the difficulty for product, that nobody tests on Libri speech, right? Or nobody tests on their exact training data. There's always some kind of mismatch. So you have to be able to incorporate like bad cases or new vocabulary items. So our tools do support decoding RNNTs with a finite state automaton with an FST. And we've been investigating that for like realistic scenarios. We continue to work on that. So, okay, so now I've summarized our system. You probably have a sense of what kinds of methods we're using. I'm going to now go quickly through some of our recent technical works. These are mostly papers, but some of them are just like things that we haven't written up yet. So pruned transducer training. Some of you might have heard about this before because we actually finished this last year sometime, but this is a faster way of doing the RNNT loss. So the issue that we're trying to solve is this, that let's suppose you have a large vocabulary size because you're using Chinese characters or something. The actual RNNT loss computation can take up too much memory. So that can limit your batch size, and then your training is too slow. So what we do basically, now the RNNT loss, it's this big two-dimensional recursion, a bit like Levenshtein distance. And it's computed over a matrix of like number of symbols by time or something like that. So, but it's actually dominated after training the system a bit. It's dominated only by some diagonal, which reflects the alignment of the data. So if you can work out the data alignment, you can compute the RNNT recursion much faster in an approximate way. So that figure on the bottom right shows you the data alignment. It shows you how the transcript aligns to the time. So if you can figure that out, what we do is we have like a simple version of the RNNT joiner that's just like a adding two vectors and a normalizing. So that one is very, very fast to compute. You can compute it with a matrix multiplication. And then if you do the RNNT loss computation on that, the output of the simple joiner, and work out where the path is, you can use those pruning bounds to basically to compute a band diagonal or a offset band diagonal and do it really fast. Anyway, so it reduces memory and time requirements. It doesn't necessarily influence the training speed a lot. That depends whether your training was dominated by the loss, and it's probably not dominated by the loss unless your utterances were super long. So another thing we have is delay-penalized transducer. So this is solving a different problem. That if you have a streaming system, the acoustic model will tend to delay the outputs. And it delays the output because the longer you wait, the more information you have. So it's better for the system to wait a little bit. I don't know if you guys can see my cursor, probably can't, but that blue line on the left-hand side shows that as you train more epochs, the delay gets worse and worse. But if you apply our penalty, it's the opposite. It gets better and it gets less and less. And those figures on the right, they compare our delay penalty with Google's fast and knit, and shows that it's generally a little bit better. The main advantage of this delay-penalized transducer, in my opinion, is that it just makes a bit more sense than that Google paper. We can demonstrate why our formulation it actually improves the loss, whereas in my opinion that the Google paper was a little bit ad hoc. Plus ours is a little bit better. So another of our papers that we've submitted to the latest conference is it's about knowledge distillation. So the idea here is it's about using systems like Hubert or Web2Vec2 or whatever to improve smaller systems. So if you want to run a reasonable size small system, you might still want to get the improvements from these semi-supervised systems or big systems. So we compute the embeddings from something like Hubert, and we predict the embeddings as some kind of auxiliary loss. And normally you would do that with something like L1 or L2, but that's kind of slow because you need to either you need to do the forward of the Hubert model, or you need to store the embeddings of the Hubert model on disk and load them. And both of those are slow because the embeddings are really big. So our idea is we kind of approximate the embeddings using a multi-codebook index approach, and we predict those indexes. And it works basically the same as L1 or L1, L2, but it's cheaper. You know. So our plan in the future is to use this in our normal recipes, so that we can hopefully dump embeddings from these big systems onto disk, and then just always train with that as an extra loss, because it gives us a little bit of improvement on word error rate. I think I don't have the results here, but it's like it gives us like 10% relative improvement. Okay, so another piece of work, we actually just released this yesterday, is something that we're calling a zip former. It's a substantially reworked version of the conformer model. And it involves a lot of different changes to the recipe. One of them is changes to the optimizer. So previously we changed the model so that each weight had its own scale. So instead of, let's say, linear 1.weight, it would be linear 1.weight times linear 1.weight scale.x. So every weight matrix would have a logarithmic scale. So we changed that to put it into the optimizer. It's a little bit more efficient, and it means you don't have to change the model anymore. You can just use like off-the-shelf auto components. And the whole optimization method, it's more stable and it lets you use higher learning rates. The other thing is temporal unit. So this is like what squeeze former does. I'm taking the name from squeeze former paper, but our downsampling and upsampling method is much simpler. It's based on just averaging or duplicating with some small changes. Another thing is to reuse the attention weights twice in each layer. So there's two versions of the attention module, but they reuse the same weights. The motivation from this is just from looking at some profiling data. It turned out that most of the time in the attention model is just computing the weights because there's multiple operations in there. So the idea is if we can reuse them twice, we don't have to pay the cost of that. We also use smaller dimensions inside the attention layer. I'm not actually mentioning all of the things, there's many changes, but another one is learnable layer bypass, so that there's like a per element or scalar scale that just bypasses each layer, and it seems to make it train better. There's more submodules per layer, so instead of like feed forward, attention, convolution, feed forward, it's like feed forward, attention, convolution, feed forward, attention, convolution, feed forward. So there's like a third feed forward, and we reuse the same attention weights in both of those attention modules. We use smaller dimensions inside the attention heads. It would be nice to have more attention heads. Unfortunately, you can't really do that because memory constraints. We want to use a large batch size. And once you increase the attention dimension past the number of heads past 8 or so, it uses too much memory. We have another innovation for stability of training I'm calling it the Y10 module. It basically adds a penalty if the covariance matrix of the features is too far from the identity. So we don't compute the eigenvalues. We just, it's based on some simple metric that's like the norm of the matrix divided by the square of its diagonal or something like that. And if that's more than one, it means that you're too far from the identity, and then you can add a penalty. The idea is that when a model diverges, if you look at the feature covariance matrix, it's often dominated by just one large eigenvalue. It just seems to be how neural networks fail. So if you can stop that from happening, it doesn't diverge so easily, and then you can use higher learning rates. Here's some word error rates from our zip former. You can see it's a bit better. So our default conformer on just LibreSpeech is giving us around 2.4 word error rate, or 2.45 with greedy search and no language model. And we get that down to about 2.17 with zip former. And we get even more improvement on test other, like from 5.7 to 5.2. So that's pretty good. And actually, this is only the early version of the zip former. I wanted to release this in time for the talk, so I'd have something interesting to talk about. But actually, I'm working on a much better version that gives us another like substantial improvement on test others. So I hope to release that soon. Actually, before I go on to Sherpa, I want to mention one other thing about ZipFormer and about the high learning rates. That I should mention that we use model averaging, and it's important if you use these super high learning rates, because if the learning rates are very high, you get a lot of gradient noise. But if you average the model over time, you can reduce the gradient noise. So, what we used to do until a couple months ago is we used to save on every epoch, and then we would average over several epochs, save models like epoch 20 through 25. But now what we do is we compute the average model from the beginning till the current point. And we compute that average, taking it every, let's say, 200 batches. And then if you have the saved average at two different points in training, you can compute a weighted combination of those two averages. And that will give you the average from, let's say, epoch 20 to 25. And that's the average taken every 200 batches. So it's a kind of finer grained average. And it gives a slightly better performance than just taking averages from epochs. Okay. Yeah, unfortunately, there's a lot more changes and details in the ZipFormer stuff. At some point, we may write a paper about this, and for now, you'll have to look in the code. But I might not write a paper about this specific version because, like I say, we have a better version that's almost ready. So I don't know if we'll reuse the name, call that ZipFormer 2, or whether we invent a new name for that. Okay. So that's our recent work, a quick summary of it. I want to talk about our inference framework, Sherpa. Actually, I might not be the best person to talk about this because it's, our guys are doing most of the work on this, especially Fang Jun, who wrote most of the work. And I only know this from a high level. I'm not as involved in the details of the code as I used to be with Kaldi, but I'll try to summarize it as best I can. So it's an inference framework for ASR. It's intended for use in products. And it's a client-server setup. The idea is you run a server program that will accept data from client processes. In the normal setup, the server is a Python process. But internally it uses C++. The idea is we want to use multiple threads, but you can't really use multiple threads in Python that are doing things that are non-trivial because of the general interpreter lock. So if we do big blocks of a computation in C++, it can release the general interpreter lock and kind of meaningfully use multiple threads. We also support a C++ only server. Some of the requirements are the normal version of Sherpa uses PyTorch's C++ library for inference. There's also a version called Sherpa NCNN that uses a different framework called NCNN for inference, but that one only supports our LSTM transducer. So whatever model you want to run with Sherpa, you need to first export it using TorchScript. Most of our things we've done with Sherpa are with models from Icefall, but we have also tested others like from WeNet or AfterVec 2.0. So some of the features of Sherpa, it supports both batch and real-time streaming ASR. It supports GPU and CPU decoding, and it does use batches in a meaningful way. So if we have a lot of streams, we'll combine all of the inference requests into batches to use the GPU efficiently. If you don't do that, you'll get very poor performance. It supports transducer or CTC-based acoustic models. So by transducer, I just mean the decoder. The encoder part of the model can be anything, it can be an LSTM or a conformer or whatever, as long as you can export it with Torch script. Of course, if you want it for streaming mode, it has to support streaming mode, and there's certain constraints about that. Like you have to find a way to pass in the recurrent state of the model. Anyway, so Sherpa supports all of the decoding methods that we normally use in Icefall, things like greedy search or fast beam search for transducer, or decoding with a graph. It can be an LG graph, like it can, you can either use a lexicon or not. Both modes are okay. Like if it was English and you had BPE lexicon, you could just build a language model directly on BPE pieces. We also recently added support for endpointing. We have some nice demos. I'm providing a Bilibili link for one of our streaming demos, which is in Chinese on the screen there. Unfortunately, I didn't want to take the risk of trying to share a video in this because, you know, sharing videos is always a little bit risky in these talks. It doesn't always work. But, you know, anyway, what the video shows is that it's very responsive. You know, it doesn't have very much latency. And we're working on having this support a large number of streams. The goal is that you can build like a robust server that will support many, many streams. Sometimes we've had, you know, bugs and things like, oh, someone runs it and it's not running as fast as they thought it would, or, you know, there's some kind of hang up. We're resolving those issues, but it's getting better and better. So it looks like that's all the material I have. If I finished a little bit early, I can try to go a little bit more into our new version of the zip former, because there's things I haven't said about that. I think we said that we were going to have questions and answers. Let me see if I can find the window that I think this Tencent meeting has some kind of window. Let me see if I can find it. Okay, I see one question, but it doesn't have a translate button.
Yeah, Daniel, maybe I can translate it. Yeah, the question is, can you hear me, Daniel? Yeah, the question is, does zip former contribute to model codification?
Model what?
Codification.
Codification.
Yeah.
I'm afraid I don't understand what the question means.
Yeah, maybe I can set the English word.
Or quantization, maybe.
Yeah.
So I believe our version of both the conformer and zip former should be easier to quantize than most conformer models. So our training programs have these options called print diagnostics. So you can print out quite detailed diagnostics of what the activations look like. And I discovered a long time ago that with a normal conformer, like a conventional conformer, usually one of the dimensions of the embeddings gets very large. Like suppose most of them are around -1 to 1 or -3 to 3. One of them might be like 50 or 100. And it seems like, I think I figured out what was happening is that it was trying to defeat the layer norm, that the layer norm was like losing the norm information. So by having one large and constant feature. So this big feature, it wasn't varying, it was a big constant, like around 50 or 52 or something, for example. Now that would cause a big problem for quantization, because if you quantize that to 5 or something, it's going to totally ruin the model. Now our modified conformer and also our zip former, that is not going to happen there, because we replaced the layer norm with something called basic norm, which is kind of like layer norm, but without the per element scales and bias, and also with a trainable epsilon. So with layer norm, it's like x divided by the norm of x plus epsilon, whereas epsilon would normally be small, like 10 to the minus 3 or something. But the trainable epsilon gets big, it's going to be like 5 or 10. So basically that removes the incentive for the model to learn this big constant offset, and then you don't get this big offset. Plus also without the trainable scale and bias, the model really isn't able to learn that offset, even if it wanted to. So basically it should be a lot easier to quantize, and I think our product group did find this, but I don't have numbers for you. Could someone translate the second question, maybe?
Okay. Daniel, the second question is, can you introduce the main idea of the scale atom and the EDEN?
Okay, so Eden is just our old, in our previous recipes, like before this week. Eden is it's the learning rate schedule. So the normal transformer learning rate schedule, it starts off at 0, it goes up linearly, and then it decreases like 1 over square root t. So the Eden learning rate schedule, the basic version starts off constant, and then it decreases as 1 over t. And there's some kind of formula there that involves both the batch and the epoch. But it's intended for use with a different optimizer, though, because before this week, the optimizer that we were using with conformer was something called Eve. And it was, it was something called Eve. It was like Adam, except that it limited the norm of each parameter tensor to a maximum value, like, so that the root mean square value of the tensor parameters was 0.1. So that stops the parameters from growing. The idea was to give you more consistent learning rates, more consistent control of learning rates, because normally parameters grow and grow during training. And then to compensate, the batch norm scales get smaller and smaller. And eventually you can have a problem with instability. So our previous approach using Eve was to keep the norms constant, but then we have these per tensor logarithmic scales that are learned. So you learn the scale of the tensor separately. And our new model from today or yesterday uses a different approach called scaled atom that puts that scale inside the optimizer. So there's now no per element scale inside the model. It's just a normal linear layer or normal convolutional layer. But the optimizer learns the scale of the tensor so that there's like a term in the gradient update that's in the direction of the current tensor, so it can either grow it or shrink it depending on the gradient direction in the direction of the current parameter. So so both of these, they require a learning rate that decreases more rapidly. So our learning rate goes like 1 over t for large T. And also in the current version, we have a brief warm-up period just for stability at the very beginning. what's the question about Kaldi and fine tuning?
Oh, okay. The third question is there any tools for Kaldi that can do the fine tuning based on the third-party pre-training model?
For old Kaldi or for next gen Kaldi? For old Kaldi, I'm afraid I'm not aware of any. It was kind of a weak point, I'm afraid, of Kaldi. I suspect that one of the reasons that that fine-tuning didn't always work is that there may have been a bad interaction with batch norm, because if the batch norm statistics change, if you change data, you could kind of expect the model to not work so well. And in old Kaldi, we used to use batch norm, but we didn't have the per element scales and biases. So it was not too easy for the model to learn to compensate for like wrong batch norm parameters. Like it would have been difficult to compensate for that. I think that may have been a reason why fine-tuning never worked that well. With the current generation, it should be, I think, easier to do fine-tuning.
Okay, thank you.
Yeah.
Yeah, and the fourth question is, did you release the paper about the zip former?
I'm afraid I don't have a paper. I think maybe I'll write a paper, or we'll write a paper about the kind of next version of the zip former, because I have a version with even more changes where we use the attention weights for a bunch of other kinds of modules. Like we have a modified version of a squeeze and excite module that uses the tension weights in that. And that seems to give some quite nice improvements. And I think we may just skip to that one. Actually, I was originally thinking of writing up a paper about our previous version of the conformer, because there was a lot of changes in there. But then because we were working on the zip former, I thought maybe we could just write up that. But now I'm going to even skip that, because like there's too many things to write up. I think I'd rather just finalize the current version and then write that up. Sorry.
Okay,
next plan of K2, any plan on unsupervised model? So, I mean, I am interested in the unsupervised stuff. One of the aims with this zip former work, what I was really trying to do is to make our training much faster. That's why it includes conformer layers that run at a much slower frequency, like 1/4 the normal frequency. So the idea is that because we have these low frequency layers, we can easily increase the number of parameters without making the training too slow. And then we can use really large models and we can use really big data. That was the idea. So it is kind of on our agenda. I want to try that with the new models. Yeah, but previously we weren't doing that because I think we didn't really have enough GPUs to run huge unsupervised model experiments. Also, like there's a question of do you really want to do unsupervised, or is it just about big data? Because you can always try to guess the transcripts, right? Like what they did in the Whisper paper. Okay.
Okay, thank you.
Yeah.
Yeah, thank you for the answer. Yeah, and thanks for your wonderful and
Cool.
amazing presentation.
Thanks.
Yeah.
Thanks. Cool. Okay, so now I think we're going to move on to Liang's part of the presentation.
Yeah.
I think maybe this last question, Liang can maybe answer.
No, this question for the comment.
Okay.
Yeah, not a technical question.
Okay,
yeah.
Cool.
Yeah, maybe. Yeah, we can move on.
Cool.
To the
Thanks,
next.
guys.
Yeah.
Bye.
Yeah, thank you. 好的感谢刚才Daniel 关于Kaldi 精彩的汇报我们后面的环节也会有关于Kaldi的一些内容感兴趣同学也可以继续提问下面我们进入对还有关于Kaldi有一个 Kaldi 的一个微信交流群，大家也可以在群里可以讨论讨论关于 Kaldi 的问题。